The recent earthquake in Myanmar has opened a new chapter in our understanding of seismic activity, particularly regarding the behavior of faults like the San Andreas. On March 28, 2025, a powerful earthquake measuring 7.7 on the Richter scale struck Myanmar, specifically along the Sagaing Fault. This devastating event resulted in the loss of thousands of lives and extensive destruction across the region. In light of this, a groundbreaking study from Caltech has utilized satellite imaging to analyze the movement of the Sagaing Fault, aiming to enhance our predictive models for future fault behavior. The findings suggest that strike-slip faults, such as the Sagaing and the San Andreas, may produce earthquakes that differ significantly from those recorded in the past, and could potentially be much more powerful. The research was spearheaded by Jean-Philippe Avouac, a prominent figure in geology and engineering at Caltech, who also directs the Center for Geomechanics and the Mitigation of Geohazards. The lead author of the study, postdoctoral scholar Solène Antoine, shared insights into their innovative approach, which was published in the journal Proceedings of the National Academy of Sciences on August 11th. The Sagaing Fault extends in a relatively straight line from north to south through Myanmar. As the two sides of the fault gradually move in opposite directions, stress accumulates along the fault line. When this stress reaches a critical threshold, it results in a rapid slip, triggering an earthquake. The similarities between the Sagaing and San Andreas faults are striking. Both are long, straight, strike-slip faults that stretch for hundreds of kilometers. Consequently, the earthquake in Myanmar provides valuable insights into the potential for future seismic events along the San Andreas fault. Antoine remarked, "This earthquake presented an excellent opportunity to apply image correlation methods, techniques developed by our research team that allow for the comparison of images taken before and after geological events. These methods enable us to accurately measure ground displacements at the fault, overcoming limitations faced by traditional radar interferometry, which can struggle with issues like decorrelation and sensitivity to north-south movements." Prior to the earthquake, researchers had predicted that a significant seismic event would occur along a 300-kilometer segment of the Sagaing Fault, an area that had not experienced a major earthquake since 1839. This prediction is rooted in the seismic gap hypothesis, which posits that sections of a fault that have remained inactive are likely to slip in order to catch up with the surrounding activity. Interestingly, while this segment did rupture during the 2025 earthquake, the fault actually slipped over a total distance exceeding 500 kilometers, indicating that it not only compensated for the previous inactivity, but also exceeded expectations. In their study, the team employed a correlation of satellite optical and radar imagery to assess the fault's movement. This technique, originally developed in Avouac's lab and now widely adopted in seismology, revealed that the 500-kilometer section of the fault shifted a net distance of 3 meters following the quake, with the eastern side moving southward by 3 meters relative to the western side. Current seismic hazard assessment models primarily rely on historical earthquake statistics and are considered time-independent. This means they can only provide probabilities of an earthquake occurring within a specified time frame. For instance, these models might estimate the likelihood of an earthquake exceeding a certain magnitude over a 30-year period in a given area. However, to make truly informed predictions about potential seismic hazards for specific future periods, such as the next 3 decades, it is essential for models to consider factors like the recency of fault movement, the locations of these slips, and the magnitude of the displacements. Avouac emphasized, "Our study indicates that future earthquakes may not simply mirror those that have occurred in the past. The sequence of ruptures along a fault even one as straightforward as the Sagaing or the San Andreas, can vary significantly and may release more energy than the accumulated slip since the last event. Furthermore, historical records are often too brief for statistical models to capture the full spectrum of possible earthquakes and their recurrence patterns. Physics-based models offer an alternative approach, with the potential to be adjusted based on observations and used for time-dependent forecasts. The research paper is titled the 2025 MW7.7 Mandalay, Myanmar earthquake reveals complex earthquake cycle with clustering and variable segmentation on Sagaing Fault. In addition to Antoine and Avouac, the study includes contributions from Caltech graduate student Rajani Shrestha, postdoctoral scholar Chris Milliner, and senior research scientist Kyung-jae Im. Collaborators also include Chris Rollins from GNS Science Te Puao in New Zealand, Kang Wang from Earthscope Consortium Inc., and Keji Chen from Southern University of Science and Technology in China. The research received funding from the Center for Geomechanics and Mitigation of Geohazards, the statewide California Earthquake Center, the National Science Foundation, and the U.S. Geological Survey. But here's where it gets controversial. Are we truly prepared for the next big quake? With the potential for future earthquakes to be so different from those we've experienced, how can we ensure our safety and infrastructure are ready? What are your thoughts on the implications of this research? Do you agree that our current models are insufficient, or do you believe they provide a reliable forecast? Share your opinions in the comments.